let's talk about something that's happening all around you right now, but you can't see it. It's this invisible shield that protects our entire digital world. It's a silent, brilliant system that makes everything from your bank transfer to your Netflix stream possible by fixing millions, even billions, of tiny errors you never even knew were there. So how does it all work? Let's get into it. I mean, really think about it for a second. You're watching a video, you're streaming some music, you're firing off an email. You're sending and receiving just an unbelievable amount of data through the air, through cables. So why does it all arrive perfectly intact? It honestly feels a bit like magic, but it's not. It's actually a genius system of self-correction. Okay, so to really understand the solution, we first have to get a handle on the problem. And the problem is this. We live in an incredibly noisy digital world, and all that noise is a constant threat to our data. It doesn't matter if your data is zipping through a Wi-Fi signal, bouncing off a satellite in space, or flowing down a fiber optic cable. That path it takes is what engineers call a noisy channel. It's just not perfect. You've got interference, physical defects, heck, even cosmic rays from space can mess with the signal. And here's the really crazy part. In the digital world, the absolute smallest error can have huge consequences. All our data, everything, is just a long string of zeros and ones. We call them bits. If just one of those little guys gets flipped by noise, a 0 becomes a 1 or a 1 becomes a 0, that can corrupt a whole file, change a number in your bank account, or create a nasty glitch in your video. So how in the world do we fight back against this constant storm of digital noise? Well, the answer lies in one powerful, elegant idea: redundancy. We build this invisible shield by sending a little bit of extra, carefully calculated information right alongside our original data. Now, the official name for this is channel coding. It sounds technical, I know, but the core idea is actually super simple. For every chunk of information we want to send, we just add a few extra smart bits. And these extra bits, they act like a protective bubble, allowing the system on the other end to check for and sometimes even fix any damage that happened along the way. Of course, there's a trade-off. There's always a trade-off, right? Because we're adding these extra protective bits, the overall speed at which we send our actual information goes down a little. We're basically sacrificing a tiny bit of speed to gain an enormous amount of reliability. And honestly, it's a trade-off that makes our entire modern digital life possible. So let's take a look at the first level of this shield. How does it actually work? We're going to start with the simplest form, just detecting that an error has happened. Think of it like a digital alarm bell going off. A classic and just beautifully simple way to do this is called the parity check. All we do is add one single extra bit, called a parity bit, to our data. And we set a really simple rule. For example, we could say the total number of ones in the final message must always be an even number. That's it. That's the rule. Okay, so let's see how this even parity rule works in practice. If our data is 1010, well, it already has two ones, which is an even number. So we just add a 0 as the parity bit. Easy. But what if our data is 1101? That has three ones, an odd number. So to make our rule happy, we add a 1 as the parity bit, which brings the total count of ones to 4, an even number. So here's the crucial moment. This is what happens when noise strikes. Let's say we sent our perfectly legal message, 10100, but on its trip, a bit gets flipped, and what the receiver actually gets is 10110. The receiver immediately does a quick count. 1, 2, 3. 3 ones. Uh-oh, 3 is an odd number. The even ones rule has been broken. The system instantly knows this data is bad and can just ask for it to be sent again. Now, that alarm bell is great for sure, but what if you're sending data to a deep space probe millions of miles away? Asking for a resend could take hours or even days. In those cases, you need a system that's much smarter, one that can not only detect an error, but actually fix it right there on the spot. And this brings us to level 2 of our invisible shield, a system that adds enough extra information to not just see the mistake, but to automatically correct it. This is where things get really cool. The most intuitive way to understand this is with something called a repetition code. And it's exactly what it sounds like. Instead of sending a single bit, we just send it 3 times. If you want to send a 0, you transmit 000. If you want to send a 1, you transmit 111. Simple, right? This is where the magic happens. Let's say the receiver gets 001. Noise flipped that last bit. Well, the system just takes a simple majority vote. You've got 2 zeros and only 1 1. Who wins? The zeros, of course. The system correctly decodes the original message as 0, and, just like that, the error is fixed. Same thing happens if it gets 1 1 0. The ones have the majority, so it knows the original message was a 1. It's a really simple but surprisingly robust way to fix a single flipped bit.
Okay, so we've seen a code that just detects errors, and we've seen one that can actually correct them. The big question is why? Why is that repetition code so much more powerful? Well, the answer lies in the concept of distance between our valid messages.
This distance is called Hamming distance. And don't let the name scare you, it's a really simple idea. It's just a way of measuring how different two digital messages are. All you do is line them up and count the number of spots where the bits don't match. So, for example, the distance between 101 and 111 is just 1, because they only differ in that one spot in the middle.
And this picture shows perfectly why that distance matters so much. Think of our valid messages, our code words, as safe zones. The Hamming distance is basically the empty space, the buffer between them. If that distance is really big, it means a noisy signal has to get corrupted a lot. It has to flip more bits before it can accidentally be mistaken for a different valid message. A bigger distance means a bigger buffer zone, which makes the code way more resilient to errors.
All right, so let's bring it all home. What have we learned? First, our digital world is just fundamentally noisy, and that makes our data super fragile. The solution is to add smart redundancy to create that invisible shield. This can be as simple as an alarm bell, like the parity check, or powerful enough to automatically fix errors, like the repetition code. And now we know the core principle that makes it all tick. The bigger the Hamming distance between our codes, the stronger that shield becomes.
And that really leads us to the final big question. You know, the simple codes we've talked about here are basically the ancestors of the incredibly complex ones used today in 5G, in satellite communications, and in your computer's hard drive. But as we demand even faster speeds and near-perfect reliability for things like self-driving cars or even remote surgery, the challenge just gets bigger. How do we keep building shields that are strong enough to protect the data of tomorrow?